Recursion is a technique where a function calls itself to solve smaller problems. The recursive case shrinks input data, drilling down layer by layer. To prevent infinite loops, a base case acts as an emergency exit, returning a definitive value to halt the cycle. Balancing these two components ensures your logic completes its task without crashing the computer's memory. This graphic breaks down the factorial of n. In mathematics, n factorial is n multiplied by n-1 factorial. In C++, our base case returns a 1 when n hits 0 or 1, and our recursive case executes the multiplication. Looking at this diagram of our physical memory space, we have an empty container on the right called the call stack. When we execute the factorial of 3, the program creates a frame for that function and pushes it onto the bottom of the stack. Since the system doesn't know the factorial of 2 yet, it has to pause the first equation. It creates a new frame for the factorial of 2, pushes it on top, pauses it, and repeats the exact process for the factorial of 1. The descent stops when we reach the factorial of 0. Our base case triggers, returning a 1, and that topmost frame pops completely off the stack. That returned value drops directly into the paused equation below it. The factorial of 1 resolves and pops, then 2. Finally, our original factorial of 3 calculates its answer, leaving the stack completely empty. Recursion does not execute multiple tasks at the exact same time. It builds a strictly ordered sequence of pauses and resolutions, managed entirely by the call stack. Here is the call stack operating without a base case. Lacking an exit condition, the program rapidly piles incomplete function frames on top of one another. Eventually, the computer exhausts the physical memory allocated for this stack. The entire process halts, throwing a runtime error known as a stack overflow. If relying on the stack carries the risk of a memory crash, you might ask why we don't just process everything using standard for or while loops. In this side-by-side comparison, the iterative loop on the left updates a single set of variables in place, keeping its memory footprint tiny. On the right, the recursive function consumes a new block of memory for every single cycle, but completely isolates the nested math. Recursion trades memory overhead for clarity, providing a maintainable way to express algorithms that would otherwise require hundreds of lines of iterative logic. This is the code for a Fibonacci sequence. The distinguishing feature here is the return statement, which requires the function to recursively call itself twice per frame, calculating n-1 and n-2. Before we execute this, take a second to picture how the system will process a dual call like the Fibonacci of 3. Does it calculate both branches at the same time? Looking at the execution tree alongside our memory space, the computer processes the left side first. It bypasses the right side entirely and drills straight down to the Fibonacci of 1. Every frame on this left path has to push, calculate, return its value, and pop off the stack before the system even acknowledges the existence of the right path for the Fibonacci of 0. Tracking this strict sequential branching behavior is the necessary first step toward mapping out advanced nonlinear data structures like trees and graphs. This rapid mapping of the Fibonacci of 4 shows exactly how logical tree branching syncs with the physical push and pop of memory frames. The larger the input, the more intricate the pause and resolution cycles become. To control this process reliably, write your base case before you write anything else, and trust the call stack to manage the pausing hierarchy. This cheat sheet captures the core trade-off. Use iteration when you need maximum memory efficiency, and deploy recursion when you need to handle heavily nested logic with clean code. Predicting these memory states gives you total control over the program's execution. By visualizing the stack, you can anticipate how functions interact and build algorithms with mathematical precision.